All right, here in chapter 8, we'll talk about periodic relationships among the elements. And this, we'll talk about this first one in a little bit more detail because it's the foundation for everything else, effective nuclear charge. So the net attractive charge experienced by a particular electron. And let's talk about this electron out here. If this is lithium, lithium has a total of 3 electrons. The first 2 electrons are in the 1s orbital. The third electron is in the 2s orbital. And you can know, or you can see right here, the 2s orbital is bigger than the 1s orbital. So this 2s electron is further away from the nucleus on average than these 1s electrons. And so the question then becomes, how much of this 3 plus charge is felt by this 2s electron? And kind of the extreme cases we could think about is, well, maybe this electron ignores these other electrons, and so it feels a full 3 plus. Or maybe these negatives totally cancel out 2 units of the nucleus, and so this feels just a +1 attraction. It ends up at somewhere there in the middle, kind of those 2 cases. These electrons between the nucleus and the outermost electron do what we call screening for the nucleus. So very, very often, all the electrons are constantly moving, but very, very often these 2 electrons are between and they are pushing the 2s electron a little bit further out from the nucleus. Okay, and that's what this effective nuclear charge is. This is how much charge that it feels from the nucleus versus the actual nuclear charge, which is easy, it's 3. So at large distances from the nucleus, the electron in the 2s orbital will only feel a net charge of +1 due to the screening provided by the other electrons. And this is a general thing. Inner electrons shield well for the electrons that are farther from the nucleus. Here's the main thing that you guys will need to know. So trends in an effective nuclear charge. The effective nuclear charge increases from the bottom of the periodic table to the top and increases from the left to the right. And these are additive, and so that the highest effective nuclear charge is over here. And the top right, the lowest effective nuclear charge is down here, the bottom left. Well, the first obvious thing that this affects is the atomic radius or the atomic size. So we can think about the size of an atom as being from the center of the nucleus to the furthermost electron, to the outermost electron. And so as this effective nuclear charge changes, how far away that electron can be is affected. And so we said from the previous slide that the effective nuclear charge is the highest in the upper right-hand side. And so we've got a teeny tiny, the smallest atom in the periodic table up here, helium. And then we said effective nuclear charge was the lowest on the bottom left. And so cesium is the largest atom. And so atomic size then runs exactly opposite to effective nuclear charge. When we have a small effective nuclear charge, we have a big atom. When we have a big effective nuclear charge, we have a small atom. Okay, and so we put those 2 trends, we see they run exactly opposite to each other. So always the biggest atoms are the bottom left side and the smallest atoms are this top right side. All right, let's talk about ionization energy. So this is the energy that is required to take any atom in the periodic table in the gas phase and then remove an electron from it. And the actual value here doesn't really matter to us. So we remove 1 electron and then we take the species that has 1 electron removed and remove a second electron. That requires about double the amount of energy. Kind of makes sense. But then we go and we try to take the 2 plus and make a 3 plus, then it's a ginormous amount of energy that's required. I just wanted to show you this this is some of the rationalization for why we've said for a while now that magnesium in all these ionic compounds is magnesium 2 plus. because removing those first 2 electrons to make magnesium 2+ is pretty easy. Then removing even just 1 more becomes very, very difficult. So this is a small step, then a huge step here. Removing each subsequent electron requires more energy. The third ionization, this one down here, requires a lot more because now we're removing an inner 2p electron. Okay, up here we were removing a 3s electron. This is also a 3s electron, but if we try to remove another, we're removing now a 2p electron, and that requires a lot more energy. That's a core electron. Okay, but here's going to be the most important thing for you guys again. So ionization energy increases from bottom to top and from left to right. What that means again, since this is additive, this northeast corner, the top right part of the periodic table, has very high ionization energies, and the bottom left has very low. So down here with cesium, cesium is very easy to ionize. Helium and fluorine and neon, those guys up here in the top right hand, are very difficult to ionize. This is also, of course, related to effective nuclear charge. All of these are. As effective nuclear charge increases, it becomes more difficult to remove an electron. All right, now we're going to go the opposite direction. This is the energy required for an atom in the gas phase to acquire an electron. So this is generic atom A. We take it, we add an electron to it, and then some amount of energy is released. The greater the affinity an atom has for an electron, the more stable, the lower energy the ion will be. As a result, electron affinity values are always negative. So let's compare 2 atoms here. So fluorine, which is really hungry for electrons, if we add an electron to it, it's an exothermic process that releases 328 kilojoules per mole of energy. Boron actually also is an exothermic process. It has a negative sign, but you'll notice it's much smaller. It's less than 10% of the previous value. It's pretty small, because this is pretty big. Okay, and so this one also fits the same trend. As we go from bottom to top or left to right, we get an increase. So again, the hot spot in the periodic table is this northeast, this top right corner, with atoms like fluorine being actually the one with the highest electron affinity. The noble gases have no electron affinity for a variety of reasons. So helium and neon and argon and all those guys, the electron affinity is 0 for them. And so what happens is as we go left to right across the periodic table, the electron affinity increases until we get to the halogens. So in this case, we get to fluorine. Fluorine's the highest, and then we go fluorine to neon. It goes to 0. The electron affinity goes down again, and then increases as we go across. All right, and then this is all those trends put together. Everything, almost, the effective nuclear charge, ionization energy, electron affinity, all have the trend that the highest part is up here in this northeast corner. The only one that's different is the atomic radius. The biggest atom is cesium. It's down here in this, I guess, southwest corner of the periodic table, bottom left. And then the other ones are the top right. All right, finally, we didn't talk much about reactivity, but I do want you to know these couple of reactivities. For alkali metals, they're very reactive, and you want to, if I give you any of those, you want to be able to balance their reaction with water. The important product that comes out here is hydrogen, and if you see any of these added to water, the hydrogen burns very easily. This gets very hot, so the hydrogen catches on fire. But giving you any of the alkali metals, I want you to be able to add water and figure out that you get the alkali metal hydroxide and the hydrogen. And then the alkaline earth metals, they're less reactive, but they undergo the same sort of reaction. So magnesium, for example, will react with water to form magnesium hydroxide and hydrogen. You'll notice the difference here is magnesium, which easily gives up 2 electrons. You only need 1 magnesium to make one hydrogen, whereas here you need 2 potassiums to make one hydrogen, because each potassium can only give up 1 electron, whereas each magnesium can give up 2 electrons.